Welcome to Final Exam Review Semester 1. Find the following limit algebraically, confirm graphically. I would like to directly substitute -5 into this. I immediately get -5 in the denominator, which in and of itself is not a big deal, provided the numerator is not 0. If the numerator is anything but 0, then we've got a number over 0 other than 0, and that is undefined, and therefore the limit does not exist. However, when I put -5 in, I get +25, I get -15, I already have -10, and I do get 0 on 0. If this is a polynomial on a polynomial, that's the best case for the 0 on 0, because it's as easy as this. If I have a rational function or polynomial on polynomial, there's a shared factor, and in this case, since -5 is a 0, x plus 5 is the shared factor. So we have to factor, but the factoring is made easy here because one of the factors must be x plus 5 to create that 0. Then I'm just going to, instead of factoring, I'm going to reverse FOIL. X times x would be x squared. 5 times -2 would be -10. And I've got 5x's minus 2x's. There's my missing 3x's. So these cancel, and this wants to be, as x approaches -5, it wants to just act like x minus 2, and that would be -5 minus 2, or -7. Now, when we get a 0 on 0, that's an indication of a hole in the graph. So we have a hole in the graph. When we get to -5, we have a hole at -7. That's what that showed to us. Now, we understand the graph of this wants to look like x minus 2. So down 2 with a slope of 1, but I've got some peculiarness. 3, 4, 5, 6, 7. At -5, -7, it wants to look like that line, but there's a hole in the graph. So let's take a look at this. I've got that preloaded, and let's go to our graph, and you'll see that on the 84, it actually appears to be indicating a hole, unless I've got some pixels missing, but that looks like it's in about the right place. Let's go ahead and second calculate a value, and I'm going to go to that was 5. I'm going to go -5.01. And I'm really close to where I believe that hole is, but it says, hey, that value exists at -7.01. But if I go -5, enter, it says, I don't know what you really are here. If I go to -4.999, it knows the value there, but it struggles at -5. So the graph of this wants to be x minus 2, but we could actually redefine this and say that this was f of x equals x minus 2 when x is not equal to -5. So same function there. All right, number 2. Define g of 4 so that this is continuous at 4. Well, that suggests it's not continuous. Let's see. Put in 4, get out 0 in the numerator. Put in 4, get 16 minus 12 minus 4, get out 0. So once again, we have a hole in this graph at 4 something. Good question would be, at 4 what? Well, really turns back into the same problem as before, where I could rewrite g of x as factors. One of those factors must be x minus 4 in the numerator and x minus 4 in the denominator, if 4 was a 0 for both. So it's x minus 4, x plus 4, some more reverse foiling. X times x is x squared, minus 4 times plus 1, we always check this, plus an x, minus 4x, minus 3x's. So this function really wants to look like this, but there's a hole at 4. But now I can find g of 4, and g of 4 would be 4 plus 4 on 4 plus 1, or 8 on 5. So that's where we would indicate the hole on our graph, and g of 4 would be defined as 8/5. That would fill in that little hole, making the graph continuous. That basically for this problem would just fill in that little spot. Okay, what should be assigned to A to make the function continuous at 3? Well, we understand this about piecewise functions. It's going to travel along this parabola until we get to 3, and then we put an open circle. And then after we travel along that parabola until we get to 3 and put it on an open circle, we're going to pass the baton to something that wants to look like a line with a, I don't know whether it's up, down, whatever. But that value could be here, but it could also be down here, it could also be down there. We need to make sure we fill in the hole. Therefore, if I put 3 into the top function, 3 squared minus 1, I need that to be the same value as if I put 3 into the second, 2a times 3, or I get 8 equals 6a, or a equals 8/6, a is 4/3, final answer, nothing to it. Okay, limit as x approaches negative infinity here. So this is like our in-model behavior test, big X test. We're trying to figure out what happens way to the left. And if I put in a huge negative, I get, this becomes a huge negative. This would be minus a big value. This would be minus again. Everything in the top is going minus further and further left, but it doesn't make any difference because it's really all about this. I can kind of ignore the rest of this. In the denominator, ignore the 4, because when x gets big, the 4 is insignificant. This graph wants to look like the limit as x approaches negative infinity of x cubed on x, which wants to be the limit as x approaches negative infinity of x squared, which wants to be positive infinity. So that limit does not exist. We would know our end model behavior if we were graphing that it's going up forever to the left. It wants to be, it wants to approach infinity out there. Okay. So does not exist. Okay, find the end model behavior, asymptote algebraically, support graphically. So end model behavior of this. We've got a second degree function on a first degree function. This wants to be a first degree function. In fact, I know that this thing wants to look like a line with slope 1. But I just don't know what the y-intercept is until I long divide this. So we got a lot to do to graph this. I'm going to go through my typical graphing process. Eventually we're going to get to this. But my graphing process, I do the 3 zeros. A. I set the numerator equal to 0. And that gives me, numerator is x minus 3 times x plus 2 equals 0. That's x equals negative 2 and 3. B. I set the denominator equal to 0, and that gives me x equals negative 3. C. I set x equal to 0, and that gives me 0, 0, negative 6 on 0, 3, negative 6 on 3. That means when I put in 0, I get negative 6 on 3, negative 2. Why do I do those? Well, those are going to reveal some important pieces for the graph, and I know that the only place that this function can be 0 is when the numerator is 0. And I know the numerator can't be, or the denominator can't be 0. This is usually indicative of a vertical asymptote. What I have to check is, do I have a match? And since negative 2 and 3 are different than this negative 3, I don't have a match. If there was a match, then it's back to page 1, our kind of discussion of where holes are in the graph. So at this point, I know I have a 0 at negative 2, and I know I have a 0 at 3, and I know I have a vertical asymptote at negative 3. And in addition to those zeros that I have, I also like to say, I also know there are no more zeros. And I kind of call these, this is like, we treat this like this is a street, and these are manhole covers, and I got the mole man partying down here, and the regular people up here, and the only way they can visit each other is through these little manhole covers. In other words, over here I'm never going to cross through 0. Nowhere else can I cross through 0. I choose x equals 0 just because usually it's a really easy way to find a point. And oftentimes we're interested in what's happening on the y-axis anyway. So 0, -2 is a point there. Okay, then I look at the big X test. And the big X test here is when I compare when I say what's happening when X gets huge. When X gets huge, it's like this problem. This would be the big X test to the left. When X gets huge, this X doesn't really matter, this 6 doesn't really matter, 3 doesn't really matter. It wants to look like a first degree equation, as I was mentioning earlier. So it wants to look like y equals x, but it could be x plus or minus something. So we have to, when the numerator outpaces the denominator, we have to long divide. So that would be x plus 3 into x squared minus x minus 6. X plus 3 goes into x squared x times x squared plus 3x, but I am subtracting those. So I get negative 4x minus 6. X plus 3 goes into negative 4x minus 4 times. And at that point, I am done. The rest of this, yes, it does not divide out evenly, but the rest of this would just be residue. In other words, once I'm done with this minus 4x, all I get is a plain old number over x plus 3. And as x gets really big, whether it's negative 6 or whatever it is, over x plus 3, as x gets big, that's going to trend towards 0. So my graph wants to look like y equals x minus 4. It wants to eventually, when x gets big, now this is when x is little right now, but when x gets big, it's going to get closer and closer and closer to this. And I believe I have enough information right here to know what's going on inside of here. And then the next question would be, to the left of negative 3, would I be in this region A, all up here, or would I be down in here, B? I fully expect to be down here in B because my mole men can't get through the street. And we'd be getting sucked into this asymptote. If it was over here, we'd need a 0 to get through there. So my last thing I might want to do is I might want to pick one point. Sometimes we have to pick a few, but we have a lot of guidance here. I'm going to find f of negative 4. And f of negative 4 would be 16 minus 4, that would be plus 4, minus 6, all on negative 4 plus 3, negative 1, and I get 20, I get 14 on negative 1. So 10, 11, 12, 13, 14, we are right down in here. And you can pick more points if you want to have a better feel. You can go ahead and put f of negative 5, but I think we got a pretty good feel for what's going on here. If we're interested in more accuracy, again, put in negative 5. For that matter, maybe you want to put in f of negative 1. Just depends on how accurate. But generally, if we want that type of accuracy, we're going to our calculators. Okay, I'm going to pause at that problem 5, and of course there will be more of these videos to follow.